Good evening and welcome everybody. My name is Obi-Wan Pez and this is N Simplex Pachinko. We are going to be doing differential equations tonight. We have with us Zach, or e to the 2i pi. If you'd like to say hello and introduce yourself.
I'm doing fine. I'm here, Zach. You did the 2i5, like you said. Yeah, I'm doing. I stream over there, and I'm here to help just make a great discussion today. It looks like we're talking about inhomogeneous systems, so get excited.
Woo! Doesn't take much to get me excited on this topic, but you know.
I was gonna say, yeah, it probably doesn't.
Okay, so on screen right now, I've got a capture of something we were working on last class, but I went a little bit beyond and did the complex non-real eigenvalue case and was able to shortcut the process a little bit by talking about fundamental sets. So as we go through this, I just want to point out a couple of quick little things. Excuse me. So I created the differential system. X vector prime is going to be equal to our transformation matrix -1, -4, 1, -1 times x vector. And as we had with the other case, I think this is the same one, is it not? Yes, okay. So this is the same one we worked on before, where we have the eigenvalues -1 plus or minus 2i, and our eigenvectors ended up becoming 2i1 and -2i1. So at the bottom we had our system. And this is fine if you're going to leave it in exponential form, but we wanted to expand this out and then talk about the real and imaginary parts separately, especially since Zach is here. We want to definitely talk about e to the 2it for some value of t. Okay.
Sorry, was that my cue?
No, I just thought I had something else going on here.
Okay. Just wanted to make sure.
Yep. So since we're looking at a differential system, which itself just has real numbers, what we really like to focus on is a real valued fundamental set. And even though it has imaginary parts in the eigenvalues and eigenvectors, this will eventually work itself out to be just real valued. And somebody might be like, well, that's kind of crazy. But the process for doing this, we're going to look at the real valued fundamental set, which is going to just be our eigenvalue. Nope, that's a vector. Eigenvector times the e portion for each of the parts. And we can just focus on 2i1, e to the -1 plus 2i times t, due to the fact that through some mathemagic as we go on through this, what we'll find is, and we actually did this last class as well, when you multiply all this stuff out and get all of the many terms that will show up, what we just ended up with was stuff that was involving sine of 2t that was real, cosine of 2t that was real, and sine and cosine of 2t that were imaginary. And the only difference between the pieces that we had was the manipulation of constants. So what I'm saying in this particular case is that we're going to look just at the fundamental set part of it and say we want all of this stuff to be real. And then once we get our fundamental set and we can show that there is a fundamental a real valued fundamental set, then we say, okay, well, we can just shift everything a little bit to have our solution be only in terms of real values. Seems a little weird, but it does work. So this is an alternate way to look at it rather than just looking at the massive breakdown of all those terms. So up top, we're going to multiply through by t into our eigenvalue, and then separate the terms as we did in the other one, where we get e to the negative t times e to the 2it, or however you'd like to do that. In this case, we do have our t is going to be a general variable, our independent variable. All right, and then we have e to the 2it is going to be equal to cosine of 2t plus I times sine of 2t. If we multiply out our eigenvector times those pieces, then we get up top 2i times our cosine. 2i times our I sine ends up becoming negative 2 sine. On the second row, we just have cosine plus I sine, all of 2t. Moving down to the next one, I separated out the real and imaginary portions, and I said that what we have here is really the sum of two vectors. One that is e to the negative t times negative 2 sine of 2t cosine of 2t, which I'm just calling u of t as a vector, plus I times e to the negative t times the vector 2 cosine of 2t sine of 2t, which I'm calling v vector. So since our fundamental set here has real valued vector solutions u and v, then the solution to the whole differential equation is going to be a linear combination of those fundamental vectors. So we end up with c1 times e to the negative t times our first vector that we had, u, plus c2 times our v vector. That should also have an e to the negative t in there, so I forgot to put that in. Arg. All right, questions, clarifications that I probably should have brought up.
Yay for fundamental sets.
Yeah, this really does shorten the work, because then you don't have to worry about all of the terms and cross terms and all this stuff. I mean, you saw how long it took me to write out all of that with the other version. So in this case, it's two rather neat columns. Alrighty. So with that, I'm gonna come over here and mark that out as the start. So Zach, last time when we talked about solutions to homogeneous differential equations, there were a certain number of terms that people had used to describe the solution that came up specifically for that. I guess you weren't here.
I was gonna say, I was here. Let's see here. I wasn't here on Wednesday. I was here Monday. So I'm a bad student, Obi. I didn't. I ditched class. I kept the class, and I didn't think so, but yeah, no. I mean, we had homogeneous. Usually called you have the homogeneous solution. That's usually what I've called it. I don't know if there's anything else you want to highlight, but.
So yes, if we're using specifically linear algebra in order to talk about it, there's another word that likes to be thrown around a bit.
Let's see here. What else do you want to use? I mean, it's the solution.
What's special about it?
Homogeneous. I was going to say, well, it's the homogeneous solution. It's the solution where you get. I mean, again, I'm trying to figure out what you want here. I'm not sure what you want. I mean, we can talk about fundamental. Are you talking about like linearly independent?
Yep. So we can get. We know that the. Yeah, fundamental set means that all of the pieces we could say like each individual solution can be considered different.
And that's where I'm using linear independence. Like you want to have a linearly independent set.
What you doing? What you doing?
Difference in some sense.
Right, and they're also considered linearly independent if what? So what does that actually mean?
So the linear independence means that like formally we say C1 V1 plus C2 V2 as many vectors as you have. If that equals 0 only for what we call the trivial solution, or that C1, C2, and all the constants are all 0. Again, I don't know how formal you want to go. That's the formal way to say it, but the informal way to say it is, as you say, different. These vectors will point in different directions.
Mm-hmm.
Which, yeah.
Right. So that's one of our major points, is that in order to get our fundamental set, in order to be linearly independent, those vectors cannot point along the same line. So they can't be, in effect, linear combinations of any of the other vectors that we see. So in the case of what we have here, a 2x2 system, or our transformation matrix is a 2x2 matrix, we're going to have two linearly independent solutions. If this is a 3x3, then we need three linearly independent solutions, and so on and so forth. But that means that the first vector can point anywhere we want as long as it's not 0 itself. The second vector can point anywhere as long as it's not along the same line, so it's got to point somewhere else. And then our third vector, if we have a 3x3 system, will need to point in a third direction. It doesn't have to be orthogonal or anything like that, but it has to be just a third direction which is not within the same plane, which will then allow us to fill out a space. Okay. So what we said was in our linear independence bit, matrices vectors are going to be linearly independent of each other. I want to make sure I get the phrasing right, because otherwise I'm going to hit myself for it later. Sorry, Zach. We said we wanted to... Oy. Of course I didn't have it right there. Cool. We want all possible linear combinations of those vectors to be equal to 0, where we're not getting 0 for the constants. Is that correct?
Right. So we want to use we only want solutions. So if we want linear independence, we want to ensure that C1, C2, and so on are all all 0.
Oh, that's the only way. Correct. Yes.
That's the only way. Yeah, that's the only way. Exactly.
So I did misspeak. All right. All right. The only way that we have C1, C1 e to the lambda 1 t plus C2, C2 e to the lambda 2t plus dot 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 out through however many c sub n e to the lambda n e to the lambda sub n t is equal to our 0 vector. Come on. Stop doing that. Is if C1 equals C2 equals dot 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 Cn equals 0. Okay. All right, so in linear algebra, there's also a special name for that.
So are you talking about linearly independent, but
True.
special for that? I mean, what's the antecedent? I don't know.
That's all right. So specifically for the fact that we're talking about having our
so the kernel here. Are you talking about mapping to 0?
Yes.
Okay.
So if this particular sum of the individual pieces, the individual solutions of our differential equation is going to map to, or is going to sum up to, a 0 vector, there's a special name that goes with that in linear algebra. I know I'm sort of vaguely prompting you, and feel free to yell at me.
Yeah, I am yelling at you. I'm
Okay.
gonna do it. I mean, so the thing that maps to 0 is called the kernel. But are you talking about? Are you talking like what specifically? I need more information.
That's all right. So,
because I feel like you want me to say something, but
yeah,
I'm not sure what I'm supposed to be saying yet.
That's all right. So that particular x vector is going to be called the nullspace solution.
Sure. Yeah. So, right, the null space of something is maps to 0, exactly. But the null space solution, I see what you're saying. Okay. I agree.
All right, because this particular vector, when we get it all set up into our solution, we can, again, say it will map to 0 if and only if all of our constants C are also 0 itself. Now, let's see here. So that does have a bit of a consequence for for our differential equation. And what we're seeing is that, okay, if we take the null space solution itself, then we're just going to plug this in. Let's call it capital X sub n as a vector. Then we end up with x sub n prime is going to be equal to our transformation matrix times our x sub n. And at this point, one of the things that we could do is comparing our two sides. Oops. If we were to subtract our null space solutions derivative, there we go, subtracted by the transformation of our null space, then we end up getting our zero vector. Another way that we can do this is you just say, look, I've got both of these pieces on the left and the right of a particular equation, so they're just going to drop out when we subtract them from both sides. The major point of this is that if we do not have a homogeneous differential equation, and so therefore our solution cannot be a homogeneous solution, right, we're going to have this non-homogeneous term which sits out in this particular differential equation. And now we have to be able to figure out how to deal with that now that we have a larger system overall. Zach, let's see. What do you know about sorry.
I was going to say, I'm hearing silence. It's radio silence.
What do you know about if we assume that x is going to be some combination then of our null space plus some other solution, which I'll get back to naming that in just a minute, but we'll call it, our non-homogeneous portion of the solution. Yeah. If we have like those two things,
right?
Yeah.
Okay.
Yeah. So if we have these things, and we just assume that we're going to have, okay, our total solution is going to be our homogeneous solution, null space solution, plus then the particular solution, then what happens when we plug this into our original differential equation?
Right, so we're going to get the... okay, so we're going to take our matrix A,
nope, let's
right?
Hang on.
We're going to have some, like... we should probably write this out.
I just did something else. What am I... Wow, okay. Yeah, there's an interesting thing that goes on with my tablet. It really, really, really wants to click the window that is behind Excalidraw. Like, no matter what it is.
Lovely.
Okay. So let's talk about this just really quickly in general. And then we'll show what happens to our actual version. So we're going to... Yep, go ahead.
Oh, no, go ahead. No,
Okay.
you were going to say something. You're fine.
So we have our x prime vector is equal to a times our x vector plus the general or non-homogeneous portion of our differential equation. And again, we want to take our solution that we had above and then fit in the pieces that we have.
That's right. So let's just put it in.
All right, what happens?
I mean, you're gonna get xn prime. And then xp prime. And since the derivatives are additive, I guess I distributed that through already.
Yeah. Why does it work with vectors?
I mean, there are linear operators.
All right, so that's really the key. Yeah.
That's really the key here is that you have a linear operator. That's great, right? That makes things very nice.
Yeah. So our derivative is a linear operator, which means that if we have, anybody who doesn't know, if we have any terms which are being added together, then we can separate those things by addition and still do the linear operator on each of those things separately. And also that if there are any constant multiples, we can just knock them out distribution or factorization. So that works kind of nicely. So derivation is a linear operator, so we're good there. We've got now big x sub n prime plus a little x sub p prime. All right, equal to.
So, and then you're going to have your axn. The A is distributive, so this is, again, a linear operator. We can distribute the matrix A to xn. However, we have to keep that on the left. We can't just can't willy-nilly change commutativity. So axn plus axp.
Yeah, super important for anybody who hasn't done any work, like significant work with matrices. The multiplication for matrices is non-commutative, at least generally, so we're not going to be changing what side it's going to be multiplied on. Super, super important. All right.
Let's continue. So, cool.
Alrighty. Now what?
Well, we know what axn is, because that is a null solution, yes?
No, I don't want to do that. Sorry. Click something. It's always dangerous to click things.
It is. It's dangerous. Very, very dangerous.
Right. So we have our x prime sub x sub n prime on the left, which is...
What is that? That's going to be just 0. Yeah, or the axn is going to be 0. That's your null solution.
Right. So in this particular case, it's not quite the same as just saying like either one of them is going to be 0, but it's the fact that these things are
they link
same.
Together.
Yeah.
Right. They link together, and so will the other part. Like the key here is that you'll have an xp prime will match up with the other two terms.
Yeah.
Correct.
So we're just going to say, much like when we were doing, who's it? Partial fraction, decomposition. We're going to say like all of the stuff that's the same in, whatever sense we're talking about is going to be equal to each other, and then the other stuff is going to be equal to each other. So in this particular case, we already knew from earlier that our null space solution is essentially just a separate solution all by itself. So we have, again, x prime sub n and a times x sub n are going to be the same thing as each other. So the reason that I popped over here and said, well, what happens if we subtract them? Oh, look, we get a 0 vector, is just to say, well, we could do that here, or you could just drop it out entirely and say,
Sure.
we've got the
Sure.
null space solution, now let's figure out
Right.
what the particular is.
Exactly. So if you, and these are going to be added in the end anyway. We're going to have our homogeneous and then your inhomogeneous solution, particular solution, or however you like. But then we can just solve this particular problem. Now.
Yep. Okay. So, what does that mean about anything that we get for our particular solution with respect to our null space solution?
Okay, I mean, I'm trying to figure out what you want me to say here. I'm still not. I'm a little.
Do you have any particular thoughts, I suppose?
I mean, like, you're going to want to solve this particular problem. That's ultimately what we're going to want to do. So solving this particular problem looks very similar into the problem we had before. And so we're going to need to do something. I mean, I have methods we could try, but again, those methods sort of depend on where you want to take this.
Mm-hmm. So I guess the first thing to discuss is what happens if you get identical things in our particular solution and our null space solution.
Then you need some sort of linearly independent solution.
Okay. So
you're gonna have to have linear independence, right?
Yep.
So you want to make sure that whatever you do, you need to make the solutions linearly independent.
Yep. So x of n, our null space solution, and x of p, our particular solution, must also be linearly independent from each other. So if we end up getting the exact same stuff, let's say e to the 2t like we had in the last one, in both parts, then we're going to have to find some way to make it linearly independent. Now, we did do that last class with Stuckey, very briefly, but we talked about it. We got we got one example down. So we'll discuss more about that when we come across it. All right, so for the one that we have here, we said that we had our null space solution from earlier. So let me just copy that through. Bring that over here. Okay. So let me also knock this out and give it the larger x sub n null space solution mark. Okay. So now we said that we need to have additionally a particular solution whose derivative is still going to be you'd think I remember it at this point. Oh no, it's over there. Okay. It's on my second monitor. -1, -4, 1, -1, multiplied by our x particular, plus e to the -2t, -2 e to the t. Okay. So, Zach, what is your favorite, perhaps easiest method to come up with solutions, particular solutions for this system?
Okay, so we've got our. I just want to check what the solutions are. So we have our null solution is e to the minus t. It's a combination of sine and cosine.
Yep.
And then e to the minus t, 2 cosine 1. Those are linearly independent. I had to check. Okay. So, and then when you've got this, so I'm looking at this and seeing, well, there's an e to the minus t term. Now I have an e to the minus 2t term, and I have an e to the t term. Those are going to be linearly independent. And I can check the Wronskian on these, right? Like you can
Absolutely.
You can double check. You can double check the Wronskian. but you should be fine because I'm looking at these and not seeing an e to the minus t. I'm not worried about any collision, if you will.
Mm-hmm. And I guess if we wanted to get really technical about it, the e to the negative t is also coupled with the sine and cosine portions.
Correct. Yeah.
So,
and that's, again, I'm not worried about it. Like,
Yeah.
there's not really anything to be concerned about. If we had an e to the minus t sine t somewhere in here, then I'd be a little more worried. Or sine 2t. Even a sine t would be okay, because we have
Right.
some difference.
some constant multiple of it.
Right. It's not strictly a constant multiple of the original. So.
Okay. So we think, anyway, x sub p should have an e to the negative 2t and an e to the t in it. And one would hope that that is going to be it for our particular solution. That we just have an e to the negative 2t and an e to the t portion at some point. Do you want to say anything about that?
I just said a thing and it was on mute. I just realized I was on mute. I said, I mean, that was my bad. But I will. No, I don't have anything to add. It's just we're gonna have an e to the minus 2t and an e to the t in it. That's all. And probably, I would imagine you're going to have a your first component and said eigenvector, or the vector here, c1 vector rather, is going to have a one in the first component versus the second component, right? If we're going to solve for, or C1, C2, however you like to think of this.
Right, so it looks like we should have, at the very least, we could say, all right, well, we're going to have a vector multiplied by each of these things in order to make sure that we just have vectors in the first place. Because otherwise, we're not going to get the, well, we're going to have a 1-by-1 matrix, and that's not cool. So our A and our B, we can just say, look, these are going to be constant matrices. If you want to break it down and say that this is going to be, you know, A1, A2, e to the negative 2t plus B1, B2, e to the t, that's also an option. It makes it a little bit easier to see. And if we're going to assume that this is our particular solution here, then what's the next step?
We need to find out what the A1, A2, B1, B2 are.
All right, how do we do it?
So let's see here. You want to so I guess we could write this as a matrix, because I mean, this really, that helps me a little bit.
Yep.
To put this together. So you'd have an A1 e to the minus 2t, B1 e to the t summed, and so on. That's just personal preference. I tend to write those together.
You put them all together.
I put them all together. So I write it as a two-vector, but, like, you know what I mean?
Yep.
But I see, what you're saying is fine. I just wanted to recognize that, and for those that are viewing this for the first time, it might be useful to see this as a vector in two space.
That's A.
That these are notationally equivalent.
Okay. Now what?
Well, if that's your XP, well, we're going to need to know XP prime.
Because?
the left-hand side.
Right. So we're going all the way back to the system itself. Oh, oops. That was not supposed to be a prime. Sorry, not that one. The one up top. Yeah, so xp prime is going to be equal to our transformation matrix times x sub p. So plug in x sub p into the appropriate locations, and then we also have our g of t vector, the e to the negative 2t, and negative 2 e to the t, all the way at the end. So just plug everything in, and if you want, you can leave it off at first. Just get everything copied down first. Alright, prime is equal to -1, -4, 1, -1, multiplied by the same vector. I just literally said same vector. That makes it way easier. We just copy it. Woohoo! Digital age. Work smarter, not harder. Alright, e to the negative 2t and negative 2 e to the t. There. Okay. What do we get for the derivative of the left-hand side?
All right, let's do this. So minus 2a1 e to the negative 2t, and then plus b1 e to the t, and then similarly below. You'll basically copy it.
Yep.
But with the change the b1 and a1 to b2, a2.
Right. All right, is going to be equal to, slightly different this time. So now what do we get?
I don't know. As Danny would say, oh, barnacles. Okay, so basically, we're gonna take. Let's see. So I'm gonna write this as minus a1 minus 4a2, all in parentheses, times e to the minus 2t. And then the
I
same
think that's
thing.
perfectly fair.
And I'm organizing this a bit in my head differently.
Well, essentially, Zach, what are you doing?
I'm doing the matrix multiplication, but I'm combining the parts that are a1, that are e to the minus 2t and then e to the t terms.
How else would you have done that?
Done that.
Yes.
Very messily by literally writing out all four terms that
oh
we'd
goodness,
be
no!
getting here.
Don't do that.
So that's what I'm saying. You could do that, and that's like I don't know exactly where you want me to go with that.
That's okay.
But I was sort of mentally like, let's group these together, and I'm just doing matrix multiplication.
So if you had left it as this, with the a1 e to the negative 2t plus, or a1 a2 e to the negative 2t plus b1 b2 e to the t, right? If you had left it as the separated added two vectors and then done matrix multiplication, yeah, you're just doing distribution. It's the same left distribution we were talking about before. It doesn't matter how you're organizing it, right? But at the same time, that would allow you to just jump a step and say, I'm not going to worry about like doing the negative a1, negative b1, then negative 4a2 and negative 4b2. So it makes it a bit easier just to say, like, organizing it even just in your head. We're taking just the a terms and doing matrix multiplication on them, doing just the b terms and doing matrix multiplication on them, and then still adding them all together at the end. So it just makes it a little bit easier to work with. Did you catch, non sequitur, did you catch Dr. Gold's last week?
I was there a few times.
Were you there for the Bessie quote?
No.
So he came out with this book, Mathematica. I'm not going to get it off. It's fine.
Okay.
And he had a huge Twitter thread that was all about, we're teaching math wrong. And he's been trying to work this out for like the last, 10, 15 years or something like that. And he said essentially the currency that we're playing with in mathematics is not axioms to then further build more and more premises and everything else like that. The currency with which we are playing mathematics, doing the math itself, is neuroplasticity. And I thought that was a very interesting take. Dr. Gold was like, oh my god, I need to go buy that book.
Yeah, I think I vaguely remember something like this. I know that this person's not the first to speak of neuroplasticity. Carol Dweck and so on are some other. It's another I think of. But yes, like there's a book by Joe Bowler about mindset and so on. So that kind of stuff has been written about before. But I've never heard of this book. I'll have to take a look at it. You can send me
possibly distilled in slightly a different way.
Sure, yeah. Well, and that's much of what we do, right? A lot of what we do is distilling things in different ways. And then, sorry, so the other ones are just going to be A1 minus A2. Thank you for saving me trouble.
If I really wanted to save you trouble, I would have done it a long time ago.
I was going to say, you really could have. And then you just add on.
Got the G vector in the end, yep.
So now with this one, you can add the constants appropriately. You could have the b1 minus b2 minus 2 now, and then a negative a1 minus 4a2 plus 1, right? So we can actually write this as one big conglomeration. Because vector addition is a thing, and vectors are very nice structures to do math in. Which, if anybody's here and is going to be a part of... When I have Real Analysis 3, like it originally was supposed to be a trilogy, but when this happens in 2025, it's a when, not if. It's just a matter of... but one of the things is going to be... The theme really is that vectors are cool and have some cool properties that make math very, very convenient. So that's like one of the big themes.
All right.
And then we can just sort of solve component-wise.
See, just like we did before when we were talking about partial fraction decomposition. Again, same deal, just like we were talking about up above. With the nullspace solution dropping out, it's because these two things are equal to each other that we can set them equal to each other in their own special equation and then worry about other stuff in its own special equation. So in this particular case, again, yeah, 100%. We're just going to take our stuff that has e to the negative 2t and deal with it, and stuff that has e to the t and deal with it. Because there's no possible way for you to get a constant multiplied by e to the t to come up with e to the negative 2t. It's just not going to happen. So, alright, this is negative a1 minus 4a2 plus 1 e to the negative 2t plus parentheses negative b1 minus 4a2. Okay, and a1 minus a2 e to the negative 2t plus b1 minus b2 minus 2 e to the t. Lovely. Okay, so at this point, again, we're going to create our own system of equations in order to break down all of our different components. So we get 2a1 has to be equal to, on the other side, negative a1 minus 4a2 plus 1. Yeah. Set it up as vectors. because, as you say, vectors are cool. Negative 2a2 is going to be a1 minus a2. Okay, and then here we just have no, not over. Goodness. a1, a2.
I do the same thing. The struggle is real there. I can't tell you how many times I've done.
Yep. We're going to just multiply everything by negative a half and clear out the constant. So I'll just stick the negative a half out front for now.
I mean, it may be wise to actually to combine stuff. I'm regretting that. I think you'll regret that choice. Because honestly, I would just write these as two equations to solve, and just to save you a little work.
That's true.
Let's see. We're gonna get.
So actually,
minus a1.
We could have also not done that.
Yeah, this is a system of equations in A1 and A2.
It would have actually been easier to combine them that way. That's all good.
I mean, do it the way you feel more comfortable with.
That's all right.
And we may be hitting the Excalibur limit here, so
yep.
Keep that in mind.
I'm sorry. I should have shared this with you.
No, it's fine. Don't. It's fine. I'm watching the stream.
Hey.
But thank you.
Yeah. I was like, well, it'd be a lot faster, so you don't have to. I was thinking, like, what am I missing?
See, I called it. I called it.
Yep. I was thinking, what am I missing? Because I was thinking, like, you weren't in here, so. Okay. Okay, so yeah, if we add a1 to the first equation and add a2 to the second equation, it simplifies things rather nicely. So we end up with a negative a1 and a negative a2, which are individually equal to a negative 4a2 plus 1 and a1. So a1 and a2 are opposites, which means that we can get a let's plug it in here. So negative a1 is equal to a positive for a1 plus 1. I don't think I meant to do that. It doesn't matter, right? It's all the same. But if we plug it in the other way, though, this will allow us to add instead of subtract. If we add a 4a2, then we end up with a 3a2 is equal to 1, so a2 is going to be a third. And therefore a1 is going to be negative.
Hold it.
Sorry.
Hold it. I'm doing something. I'm trying to catch up. I think that's a plus a2 on the top row. But below the arrow. Below the arrow. If a1 is equal to minus a2, then that means the first equation becomes... Yeah, there you go.
Right, so 5, not 3.
5, yeah.
Okay. Thank you.
No problem.
I was doing that in my head beforehand, and then somehow I just threw it out the window. Okay, so going back then, this is going to be that our x sub p is going to be a a1, a2. That's interesting, because that's not the answer I have from before. My notes must be wrong.
So the original thing was 1 I've just been sort of going along
Oh,
with
no,
you.
no, it's good.
I haven't.
It's good. Yep.
Okay.
I was looking in the wrong place. That's why.
You're fine.
Hey.
I just wanted to make sure because I'm like, well, I'm going along with you. I try not to solve these ahead of time.
Yep.
So
we can make this be a 1/5 times our vector, -1, 1. And this is going to be e to the, we said this is a negative e to the -2t. Just trying to finish too many sentences at once. Okay. Plus, we're going to do the same thing. We need a constant multiplied by our, simplified b vector with e to the t for b. So same deal here. This is going to be 1b1 and 1b2 equal to, respectively, a -b1 minus 4b2 and a b1 minus b2 minus 2. Same deal. Add b1 and b2 respectively.
yeah.
Gonna get a 2 b1 and a 2b2. Right, -4 b2. And here we're left with a b1 minus 2. So in the first case, divide 2 off from each of the pieces. Alright, b1 is going to be -2b2. So we flip the sign on this. -2b2 is going to be a negative parentheses b1 minus b1 minus 2, which is going to be equal to b1. So -b1 plus 2. Add b1 to both sides, we get 2 is equal to 2b1, and so therefore b1 is equal to 1. Alright, am I missing anything this time?
And then B2 is going to be
Opposite and twice as much.
Yeah. Half as
much. Half as much. Hey. So, yeah.
I'll be honest, that happens to me a lot myself, so don't.
Yeah.
Struggle is real.
It's great when I do it with my developmental students, though.
And so now we have an eigenvector, basically or a C1 vector. I shouldn't say eigenvector. This is a C1 vector and C2 vector for this.
Yep. So I'm going to take out a half here and then double the constants on the inside. So we get b1 is going to be 2.
Just at that. Just at that.
And b2 is going to be -1. Yeah. Alrighty. And realistically, right, we actually could have grabbed that from the relationship at least, our eigenvector, if you will, which is not an eigenvector, but the vector. Would have been from the relationship itself would have been from this line up here where we got 1b1 is equal to -2b2. These are in the same relationship to each other. It's just that our constant 1/2 out front needed to be pinned down. Okay. So now we have our nullspace solution.
And what was our original matrix?
Very good question.
I just want to make sure that we're on the. There's a lot that just happened.
Yeah. There we go.
I just wanted to make sure we have the right stuff here. Okay.
So again, we have our null space solution, which was C1. Let's just copy it. Copy it somewhere else. Hang on, where is it? Oh, just up top. Yep.
Copy paste is a great invention.
Oh yeah. With all the uses of imaginary numbers for rotating in any way, shape, or form. Not that I can necessarily rotate here, but nonetheless. Alright, so we get our null space solution, we get our particular solution, and now our total solution, if we just want to call it X vector as a whole, is going to be all of that stuff summed up. So we're going to say we got our, nope, don't do that. It's going to be our X vector. It's going to be equal to C1 e to the negative t. Negative 2 sin t, 2t. I already started, so you know. Cosine 2t plus c2 e to the negative t. 2 cosine 2t sine 2t, chicken scratch. Okay, plus, and change color just to highlight that. 1/5 times negative 1 e to the e to negative 2t plus 1/2 to negative 1 e to the t. Alrighty.
Huzzah.
We did it. So occasionally these problems do take a little bit longer, occasionally, just because we do have all of the portions that we're going to look at and say like, okay, we've got to focus on the null space solution, so now we need to get our eigenvalues and eigenvectors. Then we need to focus on the non-homogeneous portion, and with that, we used a particular method in order to find our coefficient methods, or sorry, coefficient matrices or vectors. And Zach, you want to give that one away? The name of the method is called?
Oh, this one?
Yeah.
I would have called this undetermined coefficients.
Yeah.
Or I actually learned from a professor here at my university. He called it the method of inspired guessing. And that's what...
And it is, really. I mean, we're saying, well, I'm pretty sure the solution must have a portion in it which is the same as each of the portions of our non-homogeneous portion, I'm using that word too much, of our differential equation. So using the method of undetermined coefficients, or inspired guessing, we can say, all right, I'm pretty sure that this is going to involve each of the pieces which are in this separate vector. And now let's just say each of those portions is going to have its own constant vector, and then find out what those vectors would have to be in order to get that. There is also another, I suppose, another way that we could have said, like, you know, g of t in this particular case is the portions again were e to the, come on, e to the negative 2t times a vector of 1, 0 plus a vector of 0, negative 2 multiplied by e to the t. So this would be the portion that goes into our differential equation, and we talked about earlier as, oh look, this is g. And we should be able to find, again, using undetermined coefficients, what each of those individual vector matrices needs to be. And then eventually we work it down and find it. Alrighty. So... have over here, is this all the same stuff? Looks like it. Okay. Sorry, just had, yeah, okay. Yeah, it's the same one. I was looking at 2 separate days of notes on my differential equations class, but I ended up, you know, half redoing a problem or something like that. Hey, Sensation, how's it going? Well, we spell it slightly differently. So it is not just homogeneous, unless that's what I did. Always possible that I wrote it wrong somewhere, but yeah, there's an E, at least in American.
In American.
That's what we've taken to calling it over here. Since we moved. Alright, let's see. There is also... Let's see, do I want to do that? Yeah, let's go for it. So there is also another method that we can use for cleaning up our particular systems fairly nicely, which is that if we say we want to get the particular solution... Sorry, that was lowercase in the other one. I know it doesn't really matter, but still. One thing that we can do is say we've got A times our x particular vector plus our g vector like we had before. And what we can do is let x sub p be equal to t times some other vector y, where, have to define our terms, y is an unknown vector, which we can solve for. And t is an... I'm using the word appended, but I don't think that that's necessarily true. Concatenated?
I guess what are you trying to say? You have the where y is an unknown vector and t is multiplied.
So
I would just say multiplied.
Well, no, that is true, but what we're doing to get t, like to make t in the first place, is to take our eigenvectors.
You're slamming the vectors together. Yeah. You're combining your. I mean, I guess you could say like glued. That'd be informal, but you could say appended or concatenated. I think all of those capture what you're doing. You're talking about how T is built.
Yeah.
Okay.
So in this particular case, right, T is just taking our two eigenvectors that we had, which were, let's see, we did, which way did we do it? It's down the bottom here. Oh, curses. I use the ones from the beginning. That's fun. No. I think maybe I didn't have... Yeah, that's probably okay. So what we can do is we can take our eigenvectors that we had from the very beginning. So it was 2i, 1, and negative 2i, 1, and use those instead. This is actually more likely what's going to happen in the first place. If you're going to be doing this method, you're going to be plugging a bunch of this stuff into, you know, a matrix calculator. You're not going to sit there and do it by hand. I'm only doing it by hand because Mr. Pez here absolutely loves doing stuff by hand. So, gotta show how it works first. So instead of listing our eigenvectors as like two separate things, we're just going to bring them together, snap them together like magnets, and say, there's our T matrix. So 2i, negative 2i, 1, 1. Okay. So going back to the original statement here, where we're trying to figure out what x sub p our matrix is going to be, we're going to say, let this be t times y vector, and that's going to be prime. This is equal to a times the same plus g vector. All right. Zach, where can we go from here? Like, or just algebra-wise, like, what's available to us?
Okay, so you've got some T, right? It's T vector.
Yep.
All right. Okay. So, I mean, you could try multiplying stuff. Like T is a is eigenvector matrix.
Mm-hmm.
That's what we're doing. Okay.
Yep.
So, I mean, one thing you could do is you could try to diagonalize things. Like that might be a good idea. I'm thinking about like the reason to do that is, I mean, you're basically factoring the matrix into two messy but nicer, have nice property matrices, and one really nice property matrix, if that makes sense.
Yep. How do you diagonalize?
Well, I mean, I think it's useful to talk about what this is doing. The diagonalization. You've got your T matrix. Those are your eigenvectors.
Mm-hmm.
But you're going to turn A into a product of three things. You're going to take a matrix T, but you're going to have also the inverse of T, and you'll have your D in the middle, which is your diagonal matrix. In principle, what that's doing is what's called a change of basis. I don't know how far you want to go into that, but like you're doing some transformations that will basically get me the same matrix back. And this what am I saying things you want to be going into, or
Yeah, sure.
to be quiet? No, I don't know if we want to go there, because we can.
The idea of like why this is at all important is at least nice to, even if we don't understand all of the little bits about it.
Right.
Like.
Right, and so I guess what I'm trying to say is, what I would suggest is multiplying by a T inverse, and I would recommend not on the left, left multiplication. Yeah, that does matter, doesn't it? The reason for that, and just I'm being persnickety here, but the y here is a prime alone. I don't think we need to differentiate T.
Because?
T is, what is T? T is a constant matrix.
Yeah, exactly.
You're not going to want to do that.
Even if it's in complex space, we've already figured out, like, it doesn't really matter. And anybody who's overtaking Penn's class is going to know this. But right, anytime that you've got just constants, I is also a constant, so we're just going to be multiplying a constant matrix T by our function matrix Y. And so that's the one that's going to get derived. All right, and how do you feel about associativity?
I feel great. I mean, associativity is a thing too, but that's matrices are associative, so we should be okay. And so the reason to do all this is you have T inverse AT, and then you have a T inverse G, which we'll handle in a minute. But but that T inverse AT, that basically is diagonal now. The advantage is that is going to be a diagonal matrix, and the things along the diagonal are eigenvalues, which is really convenient because diagonals along the eigenvalues are about the best as it can get. Like, you have a diagonal matrix and you try and solve this, that's at least reasonable in some sense. Now, the reasons as to why that's diagonal, I mean, if we want to go into all that, I don't know. Like, that can take some doing. But suffice it to say, this will be a diagonal matrix.
Yeah. So, let's see. At the very least, we can do the example that is sitting before us. So if we end up doing the... Oh, come on. Determinant of T is going to be 2i plus 2i, so 4i. And T inverse is therefore going to be 1 over 4i multiplied by the matrix that is, what is it, negative along the main and swap the off? Is that the cheating shortcut way?
I think that's right. You take negatives and then swap.
Yeah, oh no, it's swapping the main diagonal. Man.
Mm-hmm.
Alright. Oh well.
and then it's negatives along the...
Yep.
The other.
Okay, so then with this, gonna get a 1/4 multiplied by, and if we divide by I, that's also the same as multiplying by negative I, or I to the third.
Mm-hmm.
So we're gonna get a negative I here and I here, and then we lose the i's on the right-hand column. All right, so this is T inverse. So if we multiply T inverse by A, we get that 1/4 negative I to I2 with -1, -4, 1, -1, which is 1/4 times the matrix. So here we're going to get a plus I plus 2, and then we get a 4I minus 2. Lower is going to be a negative I plus 2 and negative 4I. Minus 2. And then T inverse AT is going to be 1/4 times all that stuff. Multiply by T again. Which is going to be equal to 1/4 times the quantity. Here we get 2I times I is going to be a -2. Okay, plus 4I. And then we get 4I minus 2 multiplied by our 1 at the bottom. No. Hang on. Did I mess it up?
Let's see. So you've got
No.
I plus 2, 4. Yeah, we should be all right on the first line.
Although I've got a problem here because now I've got a plus 4I.
Uh-huh. Well, yeah, so we could have messed up the inverse thing.
Quite possibly.
Let me think here. I forget it too, so don't feel bad. I've done so. If you can scroll over a little bit, I can try and find where the problem is. I just can't. The stroke color thing. Was in the way. So T is that. So then we're going to swap those and change the sign. That's great. T and T.
Oh. Yeah, the multiplying by negative I.
Yeah.
I didn't do that in... No. No, wait, I did. Right, because you multiply I by negative I, you get I to the 4th, so that's gone, so it's just 2's. Okay.
Yep. Yeah, you should be okay there. Yeah, okay. I'm going through and checking the math.
Yep.
Then you've got -2 plus 2. Oh. That would be okay. So look at the last line. The I plus 2, 4i minus 2 times 2i 1. That should be -2 like you have, and then 2 times wait. Right. That's fine. Yeah, no, that, and then the upper right entry should be 0. That should be fine. What you have. What you have, it looks good, actually.
Because it's right. Oh my. Yep. No, I'm good now.
And then you have the fourth. That's gonna be what does it. Because
Right,
you should get a minus 1 plus 2i.
I forgot what we were doing. I thought, oh no, we should end up with the identity matrix, but that's not what we're ending up with.
No, you're looking for diagonal entries.
Yeah,
for
yeah.
The eigenvalues. That's right.
Okay.
I was like, no, it looks
Sorry
okay,
about that.
but no, you're fine.
Here we
you're
go.
Fine.
Right,
there's a lot going on. So.
Yeah. Negative 2i times I is going to be 2. All right, then. Negative 2i times 2 is going to be a negative 4i. Then we get, again, 4i minus 2 at the bottom. Or from the bottom entry. Okay. Then down here, we're going to get same deal again. This is going to be negative I plus 2 times 2i. So we get a positive 2. And 2i times 2 is going to be a plus 4i. And then
just a moment. I'll be right back.
No problem. Minus 4i minus 2 times r1. You get that. And then the last bottom row, last column, is going to be a negative I plus 2 times a negative 2i. So we end up with a negative 2i times I squared is going to be a negative 2. Okay, and negative 2i times 2 is going to be a negative 4i. And then we get a negative 4i minus 2 times 1. Alright, there we go. So now we get a 1/4 times the matrix. Here we have at the top 8i and a negative 4. It's negative 4 plus 8i. Top right we have 0. Bottom left we have 0. And bottom right we also have a negative 4 minus 8i in this case. Okay. So then when we factor out a 4 from all of the stuff on the inside, this is going to be a 1/4 multiplied by our 4 from the inside. Gets us a negative 1 plus 2i, 0, 0, negative 1 minus 2i. Alright, so at the very least we can verify in this particular case that this inverse t times a times t is going to get us a diagonalized matrix with with our eigenvalues along that diagonal. So we end up with here, this is going to be y prime like that. This is going to be 1
I'm back, by the way.
Plus,
so just so you know.
Cool. 2i, 0, 0, 1 minus 2i. Thanks for the heads up. Times our y vector plus, and now we get again our generalized, in this case, t inverse times G. And this is one of the other things. We know what T inverse G is going to be now, because we have T inverse, it's a constant, and we have G from the very beginning. So that's going to allow us to clean up a few of these things. Everything's the same kind of math, just written differently. Yeah, pretty much. How you doing, Anders? Oh, nope, that's not Anders. That's Lizioma. I'm sorry. I forgot. You added characters at the beginning of your name. Alright, at this point, there's multiple ways to do this. In this particular case, we can break this down into two separate equations, which the first one is going to be y1 prime is equal to, and up here we get a constant 1 plus 2I times y1. It's going to be added to, and now we have to do the T inverse G, which I didn't do yet. That's fine. So we have T inverse here. So we get our 1/4, come on. Multiply by negative I, 2, I, 2, and then multiply by our G vector, which was, again, e to the negative 2t, and negative 2e to the t. Okay, this is going to be 1/4 times the matrix. And this is now going to be negative I E negative 2t minus 4 e to the t. And second, I e to the negative 2t and minus 4 e to the t. So now all that can follow us back. And then we say we're going to get rid of our matrix portion and just create two separate equations. That one's going to be down here. That one's going to be up here but slightly straighter. And then we multiply both by 1/4. Repurpose. Okay, right. And second equation is going to be 1 minus 2i times y2 plus then a quarter of all that stuff we found earlier. Okay. With all of that, what do we have here?
It looks like a differential equation.
And each of them individually look like what kind of differential equation?
Well, first order. I'm being. I mean, again, I'm sort of like.
I wasn't talking to you.
Okay.
I'm mouthing off at Excalibur, but yeah. So these are first order, and also.
Well, they're not separable.
Nope.
But you can solve them by integrating factor if you wanted.
Right, because they are first order.
Linear.
Linear. Right, so by order, or by virtue of the fact that these are now first order linear differential equations, we can solve them separately because we've done this before. This is, I will say, really gross in terms of like, there's a lot. Let me pull up Drive. I don't want to do it in that window. Let's pull up Drive over here. This is 2020-08 FA260. Wait. And there we go. 101501A. Come on. Promise I do actually want to open this. Alright. Alright. Let's show this off because it does get a little much. Recent pictures. Screenshot. Alright, so this is my work from 2020. Which I did after class because I told my students I was not going to do this in class. So I just worked on it like in my free time between stuff. Provided it decides to work. I mean, I know, Zach, you said earlier we were hitting the limit of Excalibur, but at the same time, I usually can post a picture no matter what.
Yeah, it happens.
Alright, maybe we'll break the share. Yeah, there we go. Should be the same, but we'll see. No, they changed it. Okay. Oh well. So yeah, as anybody who's in can see, this is getting a little much. In addition to the fact that I just write small when I can. We're separating out the differential equations. We end up with our y1 and our y2 here. Eventually we get to the end, and then we say, oh, by the way, x is going to be t times y, so now we take our t matrix, 2i1, negative 2i1, and multiply by the solutions to the y's we just found. And then when we boil it down, it does end up with negative 1/5 e to the negative 2t plus e to the t plus 2i times c1 plus a bunch of other stuff. In this case, it's c1 and c2 with the e to the negative 2t and e to the t. Nope, sorry. E to the lambda 1 and e to the lambda 2 that we had from before. C1 and C2 in this case are just imaginary numbers, which knock all of that stuff back to the reals. And then at the bottom we have 1/5 e to the negative 2t minus 1/2 e to the t plus C1 times e to the lambda 1 t plus C2 e to the lambda 2 t. And again, this is the nullspace solution. So we know from earlier, right, we're just going to get our x vector is going to be equal to our nullspace solution, which we said was this stuff here, plus the bits that we found here. So the matrix diagonalization method ends up finding you all of it all at once. You may have to do a little bit of cleanup at the end, and it doesn't get you the sine and cosine version unless you really go into it and, like, you know, separate everything out and break all the pieces into their appropriate parts. And eventually you end up with your e to the t cosine and e to the t sine of 2t. But it, as you can see, it takes a while. So it might not be your favorite thing to do. I don't blame you. Zach, do you have any comments on matrix diagonalization?
Matrix diagonalization is really helpful, especially when you use eigenvalues. I mean, when you take e to a matrix, I don't know, like I said, if you want to go into this, but basically taking e to a matrix with something diagonal is extremely nice, and that's what makes this whole thing possible. Really. So if we didn't have nice matrices, things would have gone very poorly. Or, like, you know, if you don't have that diagonalization done, then bad things happen. I don't know. I'm speaking gibberish right now, but basically, like, I've done enough of these problems that it can get messy. There are other methods to solve these as well that I know you'll. I was looking at your syllabus, and I know you're going to get to those things, so I don't want to say much about them now. But yeah.
And likewise, if we end up with no, that doesn't have it in it. Cool. I'm gonna start speaking gibberish too at this point. I'm okay, I promise. Right, so when we start looking at matrix diagonalization, I personally much prefer doing this with technology. I didn't really want to do all of this stuff by hand, especially, you know, coming up with our null space in terms of sines and cosines. Like, if you do it with the fundamental set method that I talked about at the beginning of this class, then it's not too bad, because it's fairly easy to just say, okay, well, we need all of these portions, and so how do we get those portions? Right, e to the t sines and e to the t cosines in some arrangement, and then figure out what that's going to be. Okay, so we have our method of undetermined coefficients. We also have our matrix diagonalization method here. And why is that here again? It's very strange. I must be missing something in my notes here. I'm sorry. This is a bit strange. Alright, we'll just do this one because it's cool. Good a reason as any. Alright, so x prime is going to be equal to, let's do, yeah, 1, 2, 2, 1 times x vector plus really? Sine of t, t. Alright, how do we work with this?
Again, you get to sort of choose your method. So which way do you want to slice this?
So, how would you go about doing this particular one, do you think? And why?
Well, I would look at its eigenvalues, and those would form my homogeneous solution.
Mm-hmm.
Right, like the eigenvalues and eigenvectors, slap on some C1s and C2s. That would give me the homogeneous solution. Once I'm done with that, I can compare what's going on in the non-homogeneous part and know whether I need do something. What I need to adjust by, if anything. But I doubt I will, because I have a polynomial and a sine of t. Those belong to sort of two different classes of things. So I'm not super worried about it. But we'll see. Who knows? There might be an eigenvalue which would throw things off.
Alright, how'd you like to solve the characteristic?
I'm doing it in my head. That might be my famous last words. But you're going to have 1 plus or minus 2. So what, 3 and negative 1 are your eigenvalues?
Alright, how'd you get it?
Algebra. Like literally just solving the,
So did you knock
add 4
this
square root.
into a second degree polynomial?
Well, no, actually I just add 4, complete the square style. So add 4 square root, making plus or minus 2, and then move things over appropriately.
Yeah. This is one of my favorite things.
Needed.
Yeah, this is one of the favorite things to do with a lot of these students, is that they're so used to like saying, oh, I need to expand this. And it blows some of their minds, not many, but some of them, to say like, you could just bring that over and say, what do you need to do? Most of my pre-calc students have generally seen, things like this, because I wanted to say like, what's the easiest method to get to a solution? Now also, what are many other methods that somebody else might have done? So we can see that there are multiple different ways that really end up getting the same result in the end. I know you're all about that.
I do enjoy having different ways of doing stuff, that's true.
No. So when we take the square root of both sides, make sure you have the absolute value is equal to 2. Yes, in theory, you could probably just say plus or minus 2 at the end, but I usually like doing this because I've got a method which we'll play around with here in a minute. We can also make this lambda minus 1 because it's interchangeable at this point. All right, factor out a negative, and we take the absolute value of that negative. So here we get Lambda is going to be 1 plus or minus 2, so yeah. What you said before.
So that actually will tell me that these are going to be real solutions, and the sine TT will be linearly independent, which is nice.
Yeah, just real quick for anybody who was curious, my method for this is like a pseudo graphical one. I do it on stream all the time, but we'll just real quick, because it's fun. I say that the difference between the number we're trying to find, lambda, and the number that's going to serve as an anchor point which is 1. I use the absolute values as a distance measurement, and so here we're saying that the distance, or the difference, between 1 and lambda, the thing we're trying to find, is 2. So that means that we travel a distance of exactly 2 in either direction, and we find where our solutions are. So upwards is 3, downwards is -1. Since it's just equal, then we want those particular numbers and no others. This also works very nicely for inequalities, because then you could say if it's less, then you need to be less of a distance away from those maximum points. And if it's greater than, you need to be further away than those particular border points. So I make a little graph out of it, and I don't know, pre-calc students seem to like it. Again, mostly because it's like showing them something that they're not used to. I think generally for pre-calc especially, that's something that we need to get into the habit of doing. Okay. So we get our null space solution is going to start with C1. We have a vector, which we don't know yet, and then e to the -t. Plus C2 unknown eigenvector e to the 3t. Right, and they are also linearly independent of G, which you said earlier. Okay. And then to get the rest of the null space solution, we have to find the eigenvectors. How are we doing that one?
Same thing with using the eigenvector or eigenvalues, put them in to the matrix you made above with the lambdas and so on.
Right, and augment with 0, 0. So when lambda is -1, we're going to get a 1 minus lambda 1, 2, 2, 1 minus lambda 1, -1, augment 0, 0. So we get a 2, 2. And then in the lowercase, we can also say take row 2, come on, minus row 1, and then put it into row 2, so we just get zeros. Alright, what does that produce for us?
Well, it says that the eigenvector is going to be 1, -1. Because we can say this is a linear system. 2x2 plus 2x1 plus 2x2 equals 0, and so we have 1, -1. C2, the V2, this eigenvector 2, is going to be similar. We just put in lambda equals 3 rather than -1.
So 1 minus 3, 2, augment 0, and 2, 1 minus 3, augment 0. So -2, 2, 0. And 2, -2, 2, 0. Okay, so again, row 1 plus row 2, store into the bottom one is just going to get us 0, 0, 0. And what's that proving for us?
So that demonstrates that our eigenvector is 1, 1.
Yeah. And whether we change all that stuff or not doesn't much matter. Again, this is going to be -x1 plus x2 is equal to 0, or then x1 is equal to x2, right? And if they're going to be equal to each other, the simplest version we can make is going to be 1, 1. All right, Nullspace done. Now what?
And then I'm gonna need to get going.
That's fine.
We just hit the 4 o'clock mark for us. And I'll probably be lurking in other chats as well. Just because that's like I'll be doing other stuff today, but it's good to be here, and I'm glad I was able to help out a little.
Yep. Thanks, Zach.
Yeah, no problem. Thank you.
Anything you want to?
No, I mean I think this is going to be interesting. I guess where are we going with this content?
Yep.
On
so,
Wednesday?
In the next couple classes, we are going to talk a bit about locally linear systems.
Okay.
And we are going to bring all of this stuff back to second-order differential equations, and how all of these methods kind of can inform how to do second-order linear differential equations, rather than, as most of the differential equations classes do, start with first order and then just run to second order and like come up with all these crazy methods.
Cool. All right. Very good.
Alrighty.
I'll see you on Wednesday.
Yep. Thanks so much.
Barring any complications, yeah.
Oh yeah.
Yeah. All right.
See you later.
Yep.
Alrighty. So then we're going to ad break. All right, everybody's back. Sorry about that. Yeah, when I'm really in the zone here, it also didn't pop up until it was too late, so like it already started the ad. Anybody who didn't catch that, Zach will be in other chats and things like that, so you can see him around with other channels that we have. Most of the time it's science communication, math communication, but as with anyone, you know, depending on how the mood is and whatever else, might pop into some other people's channels too. So what we're going to look at is finding the particular solution for this differential equation, and then once we get to the end of that one, I think we'll probably call it a night. Can we do it in the next 20 some odd minutes? Probably. I want to thank everybody for sticking around and for coming into the channel. Subway, thank you so much for following, and everybody else for stopping in and saying hi. Do we have our... Yeah. We're up to 472 followers. That's pretty awesome. We're working on the path to 500. So if you know any friends who want to learn some math content, send them on over. Alright. So, what we're going to say is now we've got our multiple different ways to find the particular solutions. I would say in this particular case, what we would like to do is to take our particular solution and say that we had an A vector times that's the vector. I don't need another vector here. Times sine of t. Plus a B vector times t. So linear function and a sine function. We did not have anything of either of those types in our non-homogeneous solution, being e to the negative t and e to the 3t. So having sine of t and t is perfectly acceptable. So with that, we want to then say, assuming that this is our solution, or at least this is what the solution is generally going to look like, then we want to plug in this particular solution, x sub p, into our into our original function, our differential equation up top. So again, if we ended up with putting our two pieces together, so having both our both our null space solution and our particular solution together, then the null space solution shows up on both sides and drops out, leaving behind everything that we're going to do here. So this was 1221 times the quantity. Alright, we'll stop the share here because this will hopefully speed it up a bit. A vector sine of t plus B vector t. Boo. Okay, plus sine of t up top and t down bottom. It's just gonna keep popping up. And just to double check. Alright, that's going to be a pain. Alright, so there's a question. I think the answer is yes. If we also include a... I can't use C because that's part of the null space. Had to use C. Right, D vector times a constant, in other words, just times 1. I think we need to include this because in addition to in addition to having... Okay. Right, if we start with a polynomial, you should then have to include all subsequent terms in that polynomial leading down to our constant. In this case, because our derivative of this thing could potentially knock out that term. Right, it's possible. So we're going to have that. Alright, then x sub p is going to be this exact same thing again. That's not what I want. Right, take this, get rid of that, and then move this one over. That prime. Okay, a sine of t is going to be a cosine of t. Oh, is that another thing? I may also need to include a cosine of t in the original g. Yeah, I do. Alright. Let's try again. Okay. So we're going to make a sine of t plus b cosine of t plus j, I know, times t plus k times 1. Okay. Nope, that was not what I wanted to... Why did you open a new tab? That doesn't make any sense. I mean, I must have hit something. Nope. Alright, hang on. There we go. Okay, copy again, paste again. Put this in here. Right. So this is going to be a cosine t plus that's going to be a minus b sine of t and then plus j, and then that's times 1. Our k vector gets cleaned out because again we're taking the derivative of 1, so that's 0. Is equal to All right, so in this particular case, we get, this is going to be a 1a1 plus 2a2 Alright, multiplied by our sine of t plus 1b1 plus plus the 1 also from here. Need to move all that stuff. You know what? We need to move all of it. So sine as well. That parenthesis as well. Alright, plus 1. Alright, b1 plus 2b2 times the cosine of t plus j1 plus 2j2 times t plus k1 plus 2k2. Alright, we'll lead on to the fact that that's going to also be in there. Alright, second one is going to be 2a1 plus a2 sine of t plus parentheses 2b1 plus b2 cosine of t plus j is going to be same deal here. It's still 2j1 plus j2, however, not vector. We're inside of a vector. Plus j2, but now we've also got the t at the end, which is going to contribute a 1 as well. So that's plus 1 all times t plus parentheses 2k1 plus k2 times 1. Same deal there. So now we get all of our separate systems of equations that are working together on this. Okay, the sine term is going to be a -1, and that's relating b's. Crap. Our sines and cosines are relating to each other, so this is less helpful, but still does something. Okay. So for sines, we get a1 plus 2a2 plus 1. It's going to be equal to, this was all nope, negative b1 minus b2. No, it's just negative b1. Never mind. Negative b1. Okay, that's sines. For the second one, we've got a negative b2 is equal to 2a1 plus a2. for cosine. We have an A1, A2. Ah, come on. No, don't freeze. Alright, well, that seems to have completely killed everything. Cool. Yep. It's dead now. Cool. Thank you everybody for coming. I'm going to utilize my moderator portion over here and try to send us somewhere. Who is on tonight? Dr. Gold is on. Yeah. Alright, so we're going to go over to Dr. Gold's stream because my stuff just screwed up. I no longer have control over... Oop, nope, there it goes. Alright, cool. Works now. Man. This is just all sorts of fun. Alright, we'll try and finish this. So, A1, A2 are respectively equal to cosine portion. B1 plus 2B2 and cosine portion 2B1 plus nope, plus B2. Okay. T. We have on the left none. So 0 is equal to the following. So on top, our T's are J1 plus 2J2. And down bottom, we have 2J1 plus J2 plus 1. Okay. And our constant is going to get us right zeros. Nope, we have J1 and J2 on the left, which are then going to be equal to top one constant is K1 plus 2K2 that's it, and bottom is going to be 2K1 plus K2. Alright, so we know the values of J1 and J2 on the left, which then we'll be able to transfer over to the right and get the values for K1 and K2. So here, this is going to be J1 can be replaced by negative J2. Negative 2 J2. So 0 is equal to 2 parentheses negative 2 J2 plus J2 plus 1. This is a negative 4 J2 plus 1 J2. It's going to be negative 3. Move it to the other side. So we get a 3. J2 is going to be equal to 1. Therefore, J2 is equal to 1/3. And if J2 is 1/3, then we get J1 is going to be negative 2/3. Negative 2/3 is going to be equal to K1 plus 2K2. And J2 was 1/3. 2K1 plus K2. Multiply this row by negative 2 and add. We're going to get a positive 4/3 plus 1 is going to be 5/3. Okay, plus a negative 2K1 plus 2K1 is going to be 0K1. Minus 4K2 plus 1 is going to be a minus 3K2. So it looks like K2 is going to be a negative 5/9. And K1 is going to be equal to negative 2K2. So that's going to be 10/9 minus 2/3, which is 6/3. This is going to be a positive 4/9. Ridiculous. All right. Alright, A1 is going to be equal to, rewrite all this stuff, it's going to be a negative 2A2 minus 1 minus B1. A2 is going to be equal to, that's not going to be helpful, so we need to get it in terms of the other one. A1, you know what? Fine. 2A1 is going to be negative A2 minus B2. So negative 2A1 is going to be positive of those. So up top, this is going to be negative 2, that's A2. No. We wanted that initially. Just Okay, we wanted A2. Negative 2A1 minus B2, which means that A2 is going to get replaced as negative 2 times the quantity, negative 2A1 minus B2, minus 1 minus B1 is equal to. All right, A1 is equal to 4A1 plus 2B2 minus B1 minus 1. Okay, so 3A1 is going to be equal to B1 minus 2B2 plus 1. B1 plus 6B2 is equal to B1 minus 2B2 plus 1. At this point, we want to keep all those things separate. We don't want to deal with any more A2s. Now we're just down to B1s and B2s. But at the same time, right, now if we plug in pretty much anything, it's going to get in terms of A's again. 2B1 is equal to negative 8B2 plus 1. not sure that I'm going to get anywhere with this. So one of the things that we can do is to plug this all into a calculator and ask it for the row-reduced echelon form of this particular matrix. So we're going to want this to be a 4 by 5, I believe. We have 4 different equations that all have A's and B's in them. What we're going to want to do is to move everything to one side, unless it has a number, in which case that's just the first matrix. And we'll go in order. So A1 is going to be a -1 if you, sorry, move it that way to get away from the 1, which is by itself over there. Then A2 is going to be a -2, B1 is going to be a -1, and B2 is a 0, and then we have 1. Alright, next equation. It's not going to matter. Let's move everything to the right near the A's. So A1 is 2, A2 is 1, B1 is 0, and 1 B2 when we move it over equals 0 because there's no constant. Cosine, we got a 1 for A1, 0 for A2, -1 for B1 because it has to move over with the A, -2 for B2, and 0 constant. Alright, 0 for A1, 1 for A2, -2 for B1, and -1 for B2, no constant. Then we go into math. Nope, we go into matrix. Math, REF of matrix A. Woo, it worked. Alright, A1 is equal to 0.1. I'll just go with fractional form because it makes a little more sense. Right, 1/10. A2 is going to be equal to -4/10 is 2/5. B1 is equal to -3/10. And B2 is equal to 2/10 or 1/5. Okay, so that means that our overall solution for this is that X bar is going to be that's the first homogeneous solution. Sorry, C2, 1, 1. did the 3t. Okay. Plus. A is going to be 1/10 times the quantity 1 - 4. And this is not E. A was... Yeah, actually it is, right. A is a sine function. Okay, plus 1/10. -3 by 2 cosine of t. Plus. J is our t function. So this is a 1/3 -2(1) times t plus 1/9 4 -5, and that's constant, right? Just times 1. Right, that is everything all the way through. And again, here we did use the method of undetermined coefficients. It makes it a little bit easier to work with. We could have used matrix stuff, but again, at this point it's getting really kind of ugly to work with all the little things that are in every individual term, or each individual term. So it gets pretty complicated when we get into it. I prefer undetermined coefficients wherever possible. There are still several different forms or different ways in which we can find our non-homogeneous solutions. So we'll get into more of those as we get further on. That was not what I was expecting. Oh, okay. I thought we did something else, and then, no, it's just, never mind. Alright, let's think, probably still, head over to Dr. Gold's. Let's see who is on. So the 9 is tonight working on the smoothest churro. Balint is going to be starting up on Microscopy Monday pretty soon. Dr. Danny Anduza is back from his dig and is now looking at the Utah dinosaur that they had. That they dug up. Irish John Games is currently working on Rise of Piracy and just about to finish this first game, so anybody who is into escape rooms and things like that. Wow, no, that is a completely different thing that I was looking at. Sorry. Anybody who might be into like piloting a pirate ship and firing cannons and doing things like that. Irish John Games. It's a good one for that. And yeah, we'll go see Dr. Gold. Been on for about 40 minutes, so makes sense. Those of you who are in the have been on his list, he does SAT prep questions, and he is going to be doing a quiz style sort of game show. So everybody head on over there and we'll see you. I will be back probably tomorrow to do some mathy type stuff. On Wednesday to do our next class of differential equations. And then I'll be back probably on Friday to play some games. Maybe some other time in the meantime. I have no idea. We'll see what I'm feeling like on any given night. So I will see you all later. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.